So we've been solving particle motion problems in this unit, and we've solved two problems so far. One where we were given a function that was easy to find an antiderivative of. A second one where we were given a function that was hard to find an antiderivative of, so we used the graphing calculator to do it for us. Let's take a look at a third style of problem that is going to ask us the same questions but require a different strategy for solution. So here at the bottom of 529, we've got the graph of velocity measured in feet per second of a particle. So notice that they give us units here. So feet per second. So we're going to want to make sure that anytime we talk about distance, we're talking about it in terms of feet. Anytime we talk about time or velocity or acceleration, we want to make sure that we're using seconds as our unit of time. So here's a particle moving along the x-axis, and the graph of the velocity is given here. So the position of the particle at t equal 8 is 12. That's just a horrible way of saying p of 8 is equal to 12. Isn't it so nice just to use proper algebraic notation? So we're going to use this graph to answer the questions that follow. The first question is, what is the position of the particle at t equals 3? So we've already solved problems like this 2 times already. So pause the video and set up this equation that we want to use in the same way that we set up the equation in the previous 2 problems. Once again, we're going to talk about the definite integral. We want to know about 3. We know about 8 as our time. So the definite integral is going to be from 3 to 8 of v of t is equal to, here they're using position, so I'll do it their way, p of 8 minus p of 3. Okay? The problem is that this time, we don't even have the function. We have this graph. So how can we calculate this definite integral given this graph of y is equal to v of t? Well, remember, definite integrals are just talking about area. It's solving the area problem. So this is an important thing for us to remember, is that we're measuring the integral of velocity, and velocity is what's measured by this graph. So that's what's going to tell us that we can just use geometry to calculate this area from 3 to 8. All right, so the first thing I'm going to do is I'll kind of break this down a little bit more. All right, so here's a little rectangle. It's got a height of 5 and a width of 1. So that area is 5. Then we've got this triangle. The height is 5 and the base is 2. So the width is 1/2 of 2 times 5, 1/2 of 10. So that's also equal to 5. And then this area down here is a triangle. It's got a base of 2 and it's got a height of, oh my gosh, let me grab a piece of paper just to make sure that we've got this right. Yep, so that is a height of 2, but it's negative. So 2 times negative 2 is negative 4, and then half of that is negative 2. Okay, so based on calculating all of those areas, what is the definite integral from 3 to 8 of v of t? Well, 5 plus 5 is 10, minus 2 is 8. So we've got 8 is equal to p of 8, which is 12, minus p of 3. And so what is p of 3 equal to? It's equal to 4. And like I say, even though they didn't use units, boy howdy, I want to use units whenever they give me the opportunity to do that. Okay? The next question they ask here is, what is the acceleration when t is equal to 5? So this is a graph of velocity. What's the relationship between velocity and acceleration? Well, acceleration is the derivative of velocity. Acceleration is talking about the change in velocity over time. So given this graph, how do we talk about here's time, here's velocity. We want to know v of t over t when t is equal to 5. How do we measure that? Remember, derivative is just solving the slope problem. So we want to know what's the slope of this curve at exactly this point. All right, and so we want to find the slope of that point. And so it's just a straight line, so we're going to calculate the slope of that segment of the line. So going from this point to this point, slope is m is equal to the change in y over the change in x, or the rise over the run. And so the rise is -5, and the run is +2. And so that's equal to -2.5. And what's the unit that we're going to use when we talk about acceleration? Well, we can think about what we're measuring here. So this is the change in y, which is velocity. So it's the change in velocity per unit time. So the velocity is changing, it's decreasing 2.5 feet per second every second. And you'll often see it in physics textbooks just written as feet per second squared. Okay? So let's wrap up the problem right here, and then we'll take a look at the two problems where they're talking about the distance. They're talking about net distance and total distance. So we're going to go back to the first page and remember what those means and apply those problems in the next video.